The Terminal, it was a movie with Tom Hanks. He lived in an airport. He lived in an airport. Oh, okay. So let's talk about terminal battery voltages. So normally when we're talking about batteries, we're talking about this is like a 9-volt battery, right? And we can say that this is the EMF. Oh, too many curls. This is the EMF, the electromotive force of this setup. And we know that's just a voltage, it's just a potential difference, okay? And normally when we talk about circuits, when we're talking about the world of physics, especially when we're drawing things on paper, this is an ideal battery. The potential drop here is 9 volts. But if you actually take a multimeter and you hook it up to a 9-volt battery, you'll see that you don't get 9 volts out of it. You get like 8.7. And that's kind of weird. So what's actually going on with the battery? Well, we know that wires and batteries themselves, they're not perfectly conductive. We know that everything has some resistivity associated with it, okay? And what actually happens is the battery itself, from one terminal to the next, is having some internal resistance or some internal resistance to that flow. So I'm not going to actually have a 9-volt battery here. I'm going to have something less than a 9-volt. And the way we can say the terminal voltage of a battery is we can say that the terminal voltage is equal to, like, in this case, 9 volts are EMF. So we'll call this E terminal. It's equal to the EMF minus IR. There is some internal resistance causing a potential drop, and we're going to lose some of that voltage in there. Okay, so let's take a look at a Kirchhoff setup, a very simple one, not much easier than what we did previously, and how it will affect this idea of a terminal voltage on a battery. So here we go. Let's just draw this real quick. Let's get some more space. If we draw this real quick, we've got a 12-volt battery, a 6.6 ohm resistor, and then let's actually hook this battery up backwards. Let's hook it up like this. So this is a 18-volt battery and a 1 ohm resistor and the 2 ohm resistor here. Okay. Now, this resistor and this battery, that is the way we're kind of writing it here. These are the internal resistances. So that 1 ohm resistor and that 2 ohm resistor there, those are the internal resistances to the battery. Sometimes they're not drawn into a circuit and they'll just tell you that, in which case you should bump them into your circuit. But if we're drawing it like this, these are technically internal resistances to the battery here. If we want to find the terminal voltage of that battery then, the terminal voltage of this first battery up here, the 18 volts, that's going to be 18 volts minus some current, and there's only one current in this circuit, so we'll just call it I, times 1 ohm. For down here, I have this in purple, the terminal voltage here is going to be 12 volts minus, and then some current multiplied by that internal resistance, 2 ohms. Okay, those are the terminal voltages we're going to have here. Now, how can we figure out what those values actually are? Well, we need to go around and we need to figure out what is the current of our circuit here. So we can figure out the current of our circuit by taking a Kirchhoff loop. So let's just do that. Let's zoom in on the circuit here and take a Kirchhoff loop. It doesn't matter what direction we go in our loop here. It doesn't matter at all. So let's just pick one. Let's just go around this direction. Okay, and then we also need to pick a direction for our current. Now maybe you've got some intuition here that the 18 volts is more potential than the 12 volts, so our current should run around this way. This should be the direction of the current, but if you pick the opposite direction, it doesn't matter. We're cool. So let's go around with our Kirchhoff loop. Let's just start right here and then work our way around. So the first thing that we have is we gain 18 volts. So I've got a positive 18 volts. And then I'm with the current as I'm going through my loop. So I'm minus I times 6.6. And then I'm going backwards across an EMF source, so I'm losing voltage, so minus 12 volts. And then I'm still going across this resistor with my current in my loop, so minus I times 2. And then minus I times 1, and that equals 0. Okay, so this is our Kirchhoff loop. So what we're... Ooh, hello. So what we're going to have here, putting things together, the 18 minus 12 is going to give us 6, and then we're going to have all the i's are like terms, and they're all negative here. So here, let's write this appropriately. So minus I times 6.6 minus 2 is negative 8.2, 9.2. So minus 9.2 equals 0. Move those to the other side. This is going to be 6 volts equals I times 9.2. Okay, and that's really just a Ohm's law we did. We just added series resistors in series to get that. This will give us a current here when we divide by the 9.2 of each side of 0.625 amps. So now that I know what the current is, I can go back to this idea of a terminal voltage. I can plug in the current for the current. I can plug in the current for the current, and we will find that the terminal voltage of our upper battery, or upper EMF, is 17.4 volts. That's our terminal voltage up there. And for our lower case, whenever we put in the 0.625 and solve that there, we're going to find it's 10.75 volts down below. Okay, so we're not actually getting the full thing out of a battery. There is some internal resistance going on in the real world. If they don't say there is a if they don't ask for a terminal voltage on a battery or a terminal EMF, then assume it's an ideal battery and there isn't this internal resistance. But if they say this is a non-ideal source, then you need to start considering what the internal resistance is going on and what the true EMF of these batteries are. Okay, so with that, we've looked at terminal voltage here. We got another Kirchhoff loop example of how to kind of set up a loop rule. And then we did another Ohm's law with V equals IR, got a current, and then ran that through. So with that, this is finished. Y'all take it easy and have a good one. Adios.